So to see how the Heisenberg uncertainty principle works in action and what it really implies, I'd like now to work through a few examples. So this will be our first example, our first demonstration, if you will, our first example of the Heisenberg uncertainty principle in action. And I believe this example actually is from Heisenberg's book. So it's a very classic demonstration of what kind of phenomena we're talking about. So the idea is this. Let's suppose we have an electron sitting somewhere and we try to measure its position. Well, how might we do that? Well, it's a microscopic particle, so maybe we would want to do something like use a microscope. So if we have a microscope, then there'll be a lens up here. This is going to be my lens, right? Here's my particle. And what I'm going to do to determine where it is I'm going to use my microscope. So that means light is going to come in. So I have to shine in some light in from the side with a wavelength lambda. The light then will hit my particle. My particle will scatter my light, and then that light will, some of it will enter the lens, right? And that occurs over a range of angles, right? The light could come up this way, and the lens will focus all of these different rays of light, of course, directly down to some focal point, which you would then observe in order to see where the particle is. Now, to measure the size of the lens, which enters into our considerations, you typically would measure then the angle theta that the lens subtends relative to the particle. So, now, the thing is that in such a setup, there is always an uncertainty in where that particle is. That's because microscopes have a limiting resolving power. And there's a classic formula for the resolving power of a lens that tells you how precisely you can be confident of the location of the particle. And that standard formula from standard wave optics is that the uncertainty in your position x, so of course this is my x-axis, is equal to the wavelength of the light that you are using divided by twice the sine of this particular angle theta. And I think you can see, roughly speaking, why we would end up with a formula such as this by considering really what you want to do to optimize the precision of your measurement, right? So to minimize, to minimize delta x, there are two things that you would want to do, right? We would want to let lambda go to 0. And I think this is understandable from your wave physics, right? If I've got a very long wavelength piece of light coming in, right, very long wavelength waves, and they're hitting this tiny particle, right, I'm not going to be able to use them to get a very good idea of precisely where that particle is because the wave itself is varying so very slowly. Rather, right, I would rather have a very short wavelength wave, right? Because then I can really tell precisely where the particle is as compared to my wave. The second thing you can see that we would want to do to minimize this quantity would be to make the denominator as large as possible, which would mean I would want theta to approach pi over 2. Now, as theta approaches pi over 2, you will notice what's happening is my lens is actually growing. If this became pi over 2, that means I have basically an infinite-sized lens. And it does also make sense, right, that a larger lens would, of course, allow you to make more precise determinations of where something is. And the fundamental reason for that is, by the way, comes from the fact that there's a diffraction limitation, which is also where this wavelength consideration comes in, right? Because if I had a very narrow lens, a tiny little spot here, once the light comes through the lens, there's going to be strong diffraction effects, which are going to smear out whatever image or focus I might obtain. So I really want as large an aperture here as possible to minimize diffraction through that aperture. And likewise, long wavelengths, particularly when the wavelength becomes sort of comparable to the size of the lens, those are definitely going to get you into trouble because, again, long wavelengths will diffract very strongly, whereas short wavelengths will show very little diffraction. So this is kind of what we would want to do if we want to optimize our measurement then of the position of our particle. Now, when we do that, though, we have to think very carefully that this may disturb in some way the momenta of my particle and lead to some confusion about what the momentum of the particle is. So let's see how this would go. So say we've done this measurement, right? And so we now have some uncertainty after our measurement of exactly where our particle is. Let's now consider some quick follow-up momentum measurements. So to do a follow-up, position measurement. So if we do this measurement, right, and then precisely determine the location of the particle immediately afterwards with a very high precision measurement, say by using a very short wavelength wave, what we would find, of course, is that we will find a range of results. Even though we think it's at one particular location, in reality, if we were to repeat such an experiment, we would be off by this amount, right? And so therefore, if we came in and then really found where the particle was, we would get some distribution of results, so the follow-up results, the results we would get, right, will of course be centered near wherever we thought we measured the particle, but there's going to be some range in those results, and that range corresponds to where the particle really was compared to where we thought it was, and that would then give this kind of an uncertainty, lambda over 2 sine theta. Okay, but what I was just really speaking about is the follow-up momentum measurement. Now, in this measurement, I think we know what we could do with our microscope, right? We would simply wait a time t and measure the new location. And I'll call that new location x prime. Now, this follow-up momentum measurement, the value I will get for it will be equal to this new position minus the initial position divided by time. That gives me the velocity, and then of course momentum is just mass times velocity. But when we do this measurement, we're going to find a spread in our results. And the reason for this has to do with the fact that after this photon comes in, transfers some momentum to my particle, so he won't have his initial momentum anymore. And then it scatters off in some other direction. And the key here is that when we see, our image focused down to a point, it's made by collecting light from all the points that hit my lens. So I won't know exactly which path the outgoing photon took when I performed the measurement. So to figure out what our final momentum is, we have to do, of course, the standard before and after collision type mechanical analysis. So we've got our before and our after. So before, I've got a photon coming in with wavelength lambda, and my particle itself may have had some initial momentum px. Afterwards, my particle is going to be moving along, and I'm only really thinking right now about the x component of its momentum. I know it's going to pick up a y component, so maybe I'll be more precise. So afterwards, right, my light will be coming up with a wavelength lambda. At some angle, I don't know exactly what it is, right, but it has a maximum range of plus or minus theta. And then my particle itself must be traveling down with some other momentum. And my main concern is to figure out what is this new momentum in the x prime direction. So, to determine the final momentum in the x prime direction, we simply write down conservation of momentum in the x direction, so conservation of px. The before momentum in the x direction was the momentum of this incoming light, right? And so it was coming in with momentum h over lambda from our de Broglie hypothesis, plus there was whatever x component of momentum my particle may have had. That's then going to equal now, the tricky part is the outgoing momentum of my photon, right? I'm assuming you'll notice it's coming out with exactly the same wavelength. Now, we've just been through Compton scattering, and it's true, there will be a very small shift in this wavelength. If I'm using, for example, visible light, the Compton shift in the wavelength will only become relevant at extremely high energies if we were using gamma rays. So we'll just put that aside for now and simply say that the outgoing photon here has essentially the same wavelength as the incoming photon. So if I get the x component of this now, it's going to be h over lambda is the magnitude of that total momentum. But for the x component, I need to multiply by sine of theta. And, of course, I don't know exactly what theta is. It could be 0. It could be the same theta from the lens. It could be the negative theta from the lens. So this is uncertain over a range plus or minus, actually, h sine theta over lambda. And then, of course, there's the outgoing x component of my momentum, which I will call px prime. Now, there's also the equation for conservation in the y direction, but I have all the information I need now. So my final follow-up measurement is going to give me a measurement of this p prime x. And what I want you to notice is I can solve here, right? It will be the initial x momentum of my particle plus the h over lambda that it picked up because it collided with this incoming photon. And then the outgoing photon, though, is what creates this uncertainty. I put this onto the other side of the equation to solve for px prime. I get minus or plus h over lambda sine theta. So I'm going to get results in some kind of a distribution. I don't know what the final shape of this would look like, but it would certainly be centered around this px, right, plus h over lambda. But then there's going to be a range of results, you know. So what I'm trying to show you here actually is the probability distribution for this momentum measurement. It'll, be maybe constant, right? Because I get, a fairly wide range of these angles in here. I don't know the exact shape of the probability distribution for capturing these different angles, but I seem to be able to cover all angles very well because of the way the lens focuses things. And so after I go this range of plus or minus, it's going to, drop down like so, right? And this range, again, of these outgoing momenta that is uncertain for me is minus or plus. Well, the actual size of it is the magnitude here, h over lambda times sine theta. So therefore, the follow-up measurements are giving me a range of x components of my momenta that are about equal to h over lambda times sine theta. Now, once again, this is the last time I'll emphasize this, but remember, I haven't defined this probability distribution. I haven't actually done the variance calculation to get the standard deviation. I'm just eyeballing or estimating things here, but this seems to be the width of my distribution. Okay, so our follow-up position measurements we see will give us a range of values. Our follow-up momentum measurements are giving me also a range of values, so follow-up momentum measurement. And now I can check my product. And notice these things seem to be in tension, right? To minimize delta px, we can see the physical effects in tension, right? To minimize my delta px, I would want to send lambda to infinity. And you can see that would be a very good thing because then I would have these very long wavelength, low energy photons that carry essentially no momentum. So they're not going to transfer anything to my particle. So there won't be this much effect at all from these collisions, and I would get a very narrowly defined momentum distribution. Also, what I would like to do is I would like to let the angle theta go to 0. And you can see why that would be nice, because if my lens doesn't span over a wide range of angles, right, if it's just really almost like a point, then there's no uncertainty in the momentum because I knew the incoming momentum and I know the outgoing photon went essentially straight up. But of course, these are both exactly the opposite of what we wanted for a good position measurement. So there's always this tension, right, where the uncertainty that's reflected in these follow-up measurements and the distributions that we see show the initial measurement wasn't as precise as we would have liked it to be, and to optimize either the position or the momentum, the knobs we turn are in complete tension with each other. And the final product, so the final product is what we want to check. And you can see then our delta x times delta p, in this case, will equal lambda over 2 sine theta, was my diffraction limitation. My momentum uncertainty, as we just saw, was h over lambda times sine of theta. Right? And they're going to see we have quite a few cancellations here. Particular, the sines of theta cancel, the lambdas cancel very nicely, and we get, in this case, approximately h over 2, which is, of course, very safely greater than or equal to the true fundamental limit, h bar over 2. So I hope this gives you an idea then of the types of things that go on and what, in terms of the tension between precision measurements of momentum and position, and what really then the underlying meaning of this Heisenberg uncertainty principle seems to be.